In this video, I will give some hints towards solving an exercise based on real experimental data for size exclusion chromatography, SEC. A 6 mm per minute feed containing 8.8 gram per liter of PEG and 0.43 gram per liter of benzoic acid is separated using a 40 cm long SEC column with a diameter of 4 cm. A. What is the void fraction? B. What is the porosity of the gel? And C. If the outflow is collected during the time between when PEG starts to come out and when the time benzoic acid reaches 50% of the inlet concentration, what will then the ratio between benzoic acid and PEG be in the outlet? So these are the breakthrough curves. Note that since this is size exclusion chromatography, we have two breakthrough curves. One for the large molecules that comes out first, in our case PEG, and one for the small molecule that come out later, since these molecules can enter into places where the big molecules can't. In our case, the small molecule is benzoic acid. Our first task is to calculate what you might call the capacity of the column, but a better terminology is to say that we need to determine the void volume and the pore volume of the column. The area above the breakthrough curve for the large molecules is proportional to the void volume, while the area above the breakthrough curve for the small molecule is proportional to the sum of the void volume and the pore volume. In this graph, it seems like the area above the breakthrough curve for the large molecule is much more larger than the area of the breakthrough curve for the small molecule. How can that be? Surely the sum of the void volume and the pore volume must be larger than the void volume, right? If you get a bit confused now, don't worry, because that's very common. I said that the area above the breakthrough curve is proportional to the volume, but we need to consider the units in this graph really carefully to translate this area to a volume. On the y-axis we have millivolts, and on the x-axis we have minutes. Thus the area has the strange unit millivolt minutes, which is clearly not a volume unit. So you need to figure out how to translate millivolt minutes to the milliliters or some other volume unit. In doing that, you need to make some kind of assumption regarding how millivolt is related to concentration, and I suggest you make the simplest possible assumption. Once you have correctly translated to volume units, you will notice that the sum of the void and the pore volume is indeed larger than the void volume. To calculate the area quickly and manually, we first determine Tstore using a visual comparison of areas. We draw a vertical line and compare the area above the breakthrough curve to the right, that is later than our vertical line, with the area below the breakthrough curve to the left of our vertical line. We move the line back and forth until we find a spot where these two areas have the same size. Once you have done this for the breakthrough curve for the large molecules, you repeat the process and determine Tstore for the breakthrough curve for the small molecules. Note, when you do this visually, you don't get an exact answer, but you can get a surprisingly good accuracy, and in our course that's good enough. In real life, making a visual evaluation of a breakthrough curve in this way can be a good way to test that your advanced chromatographic system seems to be doing calculations correctly, the way you want it to do. In this exercise, you are actually not asked to tell what the void and pore volumes are as such, but rather what the void fraction is and what the gel porosity is. The void fraction is simply the void volume divided with the total volume of the column. Regarding the gel porosity, the difference between the total volume of the column and the void volume must be the volume of the gel. Since you can determine the pore volume by comparing the two breakthrough curves, you can determine the gel porosity as the pore volume divided with the gel volume. In the last subtask, you are asked to determine the benzoic acid to PEG weight ratio in the outflow. So how do you do that? Well, first you need to determine the breakpoint, and in this task you are asked to select the breakpoint as the point when the concentration of benzoic acid in the outlet is 50% of the inlet concentration. So to calculate the mass of benzoic acid in the outlet, you have to determine the area under the curve. And the simplest way to do that is probably to find a triangle that has the same area as the odd shape below the breakthrough curve. When calculating how much PEG that has come out, there are different ways to do that in this exercise. The quickest way is likely to realize that you already calculated the void volume and that you have passed the saturation point. That is, the breakthrough curve is already at its highest point. If you don't understand how to use that information, you can instead just determine the area under the breakthrough curve for the large molecules up to the breakpoint and get to the PEG weight that way. I recommend you all to also try to figure out the answer to this question. Does it matter for the benzoic acid to PEG ratio if you start collecting the flow in the outlet at t equals 20 minutes, or if you start collecting at t equals 0 minutes?